Good morning, grade 9. We're going to continue today the lesson that we started yesterday. The lesson, chapter 5, lesson 4, rational functions. If we had a quick review about the lesson, yesterday we studied the rational function f of x is equal to 1 over x, and there is a rational function, the formula that is f of x is equal to a over x minus h plus k, a over x minus h plus k, where a represents the absolute value of a represents vertical stretch or compression factor, and if a is negative, it represents reflection across x-axis. And k represents vertical translation. If k is less than 0, if k is negative, so it is down. If k is greater than 0, so it is positive, so it is up. The vertical translation is up. And about h, h represents horizontal translation. It is to the left if h is less than 0, if it is negative, and it is to the right if h is greater than 0, which is positive. And I want to remind you that the original rule contains negative sign, so h value is the opposite of the sign that is in the function. And then we solved some problems, and then we had the rational functions. For rational functions of the form f of x is equal to a over x minus h plus k, the graph is a hyperbola. This is the name of the graph of the rational function, like the parabola, okay, for the quadratic function. But for the rational function, it is called hyperbola. And there is a vertical asymptote at the line where x is equal to h, and the domain is written in this form where x is not equal to h, and there is a horizontal asymptote at the line where y is equal to k, and the range is written in this form where y is not equal to k. Okay, the new part that we're going to study today is called a discontinuous function and a continuous function. A discontinuous function is a function whose graph has one or more gaps or breaks. A discontinuous function, disturbance happened in the function, disturbance happened in the graph. So it has one or more gaps or breaks. The hyperbola graphed above and many other rational functions are discontinuous functions. The hyperbola graphed above. Okay, the hyperbola graphed above. What about a continuous function? A continuous function is a function whose graph has no gaps or breaks. It is continuous. That's why it is called continuous. Has no gaps or breaks. The function you have studied before this, including linear, quadratic, polynomial, exponential, and logarithmic functions, are all continuous functions. So all the functions that we have studied before are continuous, like linear, quadratic, polynomial, exponential, and logarithmic functions. They are all continuous functions. But in the rational functions, it can be discontinuous function or it can be continuous function. The graph of some rational functions are not hyperbolas. Consider the rational function f of x, x minus 3 and x plus 2 over x plus 1. And its graph, the numerator of this function is 0 when x is equal to 3 or x is equal to negative 2. The numerator of this function is 0. Why? If x is equal to 3, so 3 minus 3 is 0. So 0 multiplied by x plus 2 is 0. So 0 over any number is 0. So the numerator of this function is 0 when x is equal to 3 or x is equal to negative 2. Therefore, the function has x-intercept at negative 2 and 3. The denominator of this function is 0 when x is equal to -1. As a result, the graph of the function has a vertical asymptote at the line where x is equal to -1. Where x is equal to what? To -1. Because we mentioned before that the vertical asymptote where x is equal to h in the denominator. So here the denominator is x plus 1, so the value of h is the opposite of this sign where h is equal to -1, so it has a vertical asymptote at the line where x is equal to -1. Okay, zeros and vertical asymptotes in the rational functions. If f of x is equal to p of x over q of x, where p and q are polynomial function in standard form with no common factors other than 1, then the function f has zeros at each real value of x for which p of x is equal to 0, and then a vertical asymptote at which real value for x for which q of x is equal to 0. Again, if I have a function f of x is equal to p of x over q of x, where p and q are polynomial functions, f of x is equal to p of x over q of x, where p and q are polynomial functions. So f of x has zeros at each real value of x for which p of x is equal to 0. And also it has a vertical asymptote at each real value of x where q of x is equal to 0. So it has a vertical asymptote at q of x is equal to 0, and it has zeros at each real value of x where p of x is equal to 0. Let's here solve an example that will clear everything. Graphing rational functions with vertical asymptotes. Identify the zeros and the vertical asymptote of f of x. X squared minus 2x minus 3 over x minus 2. Step 1. Find the zeros and the vertical asymptote. First, I'm going to factor x squared minus 2x minus 3. It will be x plus 1, x minus 3. Okay? Then factor the numerator. We factor the numerator. Then the numerator is 0 when x is equal to -1 or x is equal to 3. Yes, because the zeros for this function is -1 and 3. X plus 1 is equal to 0, so x is equal to -1. X minus 3 is equal to 0, so x is equal to 3. So the zeros here is equal to what? To -1 and 3. Okay? And the vertical asymptote is equal to 2. Opposite of this sign. Okay, girls, so the first step, we're going to factor the numerator. Then find the zeros. The numerator is 0 when x is equal to -1 or x is equal to 3. So the numerator is equal to 0. If I make the numerator is equal to 0, in which values it will be equal to 0? If x is equal to -1, so -1, +1 will be 0. So 0 multiplied by anything will be 0. So the numerator will be 0. Or by x is equal to 3, because 3 minus 3 equals 0, so 0 multiplied by anything will be 0. The vertical asymptote is the value of h, down, which is the opposite of the sign here, -2, which is 2. And then I'm going to graph it, plot the zeros, and draw the asymptote, then make a table of values to fill in the missing points. I will choose points from my mind: -4, -1, 0, 1.5, 2.53, and 5. Okay, girls, then I will substitute the value of x. If it is -4, I will substitute here -4, -4, -4 to get its value, the value of y. So it will be -3 and 0.5. Then if I choose -1, so I will substitute -1, -1, and the value of y will be 0. Then I will substitute x by 0 and then get the value of y. I will substitute x by 1.5 and get the value of y, and so on. Let's watch a video together.
All right, let's see if we can graph one of these bad boys and see all the pieces coming together in action. You want to graph this particular rational function. The first thing I would suggest that we do is see if we can factor. So let's see if we can clean this up a little bit. I see that actually the numerator is just x minus plus, and I guess a 2 and a 1. Okay, now that helps me a little bit, because first of all, I can find asymptotes. So let's find asymptotes. So vertical asymptote, that's an x value, which make the denominator equal to 0, so x equals -1. Now what about the horizontal asymptote? Well, now this is not of that nice simple form that we saw earlier. So here's the rule. For horizontal asymptotes, what you do is you look at the highest exponent appearing in the numerator, the highest exponent appearing in the denominator. If the highest exponent in the denominator is greater than the highest exponent in the numerator, then in fact you're going to have a horizontal asymptote at y equals 0. Simple. So if the polynomial in the denominator has a greater degree than the polynomial in the numerator, y equals 0 is your horizontal asymptote. Move on. If the degree of the polynomial in the numerator is greater than the degree of the polynomial in the denominator, as in this case, then in fact what you see is that this will have no horizontal asymptote. You can kind of see that if you think through it a little bit, because what happens is the x's get really big, right? Horizontal asymptote is asking what happens as you go off to the horizon. Well, as the x's get really big, basically subtracting 2 from a ridiculously huge number is not going to do anything, so it's negligible. In fact, adding x is not nearly as powerful as x squared. So the dominating term here, is x squared. The dominating term downstairs is plainly the x. If x is getting really big, adding 1 is not going to do anything. So the dominating terms are given by those highest powers. And so what do you see here? You see an x squared over x. Well, x squared over x, if you sort of squint your eyes, is just x if you simplify. So as the y's get big, as the x's get bigger and bigger, y is kind of acting like x. So it's going off. It's getting bigger. So it's not landing to an asymptote. It's sort of going off, getting bigger and bigger with x. So therefore, no horizontal asymptote. So if the degree of the numerator is greater than the degree of the denominator, no asymptote. Now, there's one case left over. What happens when the degree of the polynomial in the numerator equals the degree of the polynomial in the denominator? Well, then it's sort of like a tie. And so you have to go into sort of like a special round, right? You have to go into sort of a runoff. And what you do is, in the runoff, what you do is you just look at the coefficient of the term with the highest power in the numerator divided by the coefficient of the term with the highest power in the denominator, and that ratio, that fraction of coefficients is your horizontal asymptote. So y equals a over b, wherever the a is the coefficient on the leading term and b is the coefficient of the leading term in the denominator. Anyway, lots of stuff here, whereas in here we see the degree in the numerator is greater, so it dominates, and so there's no asymptote here, no horizontal asymptote. Okay, great. While we're here, let's actually find the zeros. Remember what the zeros of any function is. It's where, in fact, we cross the x-axis. What values of x make the 0? That's easy. Just look at the numerator. When do I make that? How do I make that 0? Well, if x equals 1 or if x equals -2. So the zeros, which are sort of fun points, x equals 1 and -2. That's where it's going to cross the x-axis. All right, well, armed with that, I claim we can actually plot a really accurate graph, but you might want some extra points, so we can make a little table up here. Various points for x, and finding the corresponding values for y. Well, a few of these we know already. For example, at 1, we know it's got to be 0, because we have 0 on top divided by 2, so that's 0. It's one of the zeros. Also, -2, we know it's 0. And you can plug in -5 into here, and you'll see -4.5, -2, -2, 2.5. Really? -2 for 0? Sure. Plug in x equals 0. What do you get? 0, 0, -2 divided by 0 plus 1. So -2 over 1 is just -2. And they all check out. Who cares? All right, let's plot these points. I'm actually going to save these points for the last because I want to show you that really this is the key idea. First, I put down any asymptotes I have and mark them carefully because they're going to cut up the world. So I have a vertical asymptote at -1. That means right here, and I usually denote that with a dotted line. There's no horizontal asymptote, so I cut the world up into just two pieces. You see, the left and the right piece. All right. Now, what do we know? We have zeros, so we know that x equals 1 is a 0, and x equals -2 is a 0. And now I know I'm going to be approaching this asymptote, but I don't know how, and that's where these points come in handy. Let's plot some of these points. So at -5, I'm at -4.5. So let me slide this down here. -4, -5, -4.5 is right here. -5, so there's that point. At -3, I'm at -2. And then at -2, I'm at 0. We already had that. Now at 0, I'm at -2. So at 0, I'm at -2. It's right here. At 1, I'm at 0. We knew that. And at 3, I'm at 2.5. 2, 3.5. So 2.5 is right there. And those points allow me to put this together, knowing that I'm an asymptote here, and knowing there's no horizontal asymptotes. I'm never going to level off. And so what I see here is the following. Heading to the asymptote. And the same thing here. Really interesting looking hyperbola. You can see I keep dropping down. I'm never going to sort of land. I keep going up, soaring up into space, never going to actually land either. And yet I want to kiss this asymptote right here because I'm heading toward it as I go up and down. And I can see that I'm going up here and down here because of the points. Pretty cool. Pretty cool.
Okay, girls, back to our book. We have some rational functions, including those whose graphs are hyperbolas, have a horizontal asymptote. The existence and location of a horizontal asymptote depends on the degrees of the polynomials that make up the rational function. Note that the graph of a rational function can sometimes cross a horizontal asymptote. However, the graph will approach the asymptote when absolute value of x is large. So here we have some rules for the horizontal asymptotes. Let f of x is equal to p of x over q of x, where p and q are polynomial functions in standard form with no common factors other than 1. The graph of f has at most one horizontal asymptote. At most, maximum one horizontal asymptote. If degree of p is greater than degree of q, there is no horizontal asymptote. If the degree of polynomial of p is greater than the degree of polynomial of q, there is no horizontal asymptote. If degree of p is less than the degree of q, the horizontal asymptote is the line where y is equal to 0. Again, if the degree of polynomial p is less than the degree of polynomial q, then the horizontal asymptote is the line where y is equal to 0. If the degree of polynomial p is equal to the degree of polynomial q, the horizontal asymptote is the line where y is equal to the leading coefficient of p over the leading coefficient of q. Let's go to the next page to see an example that will make it more clear. Example 4. Identify the zeros and asymptotes of each function. Step 1, I have to factor. So it is 80, which two factors, if I multiply them together, they will give me -6, and when I add them together, they will give me the middle term, which is +1. It is +3 and -2. So the zeros of the function is x plus 3 is equal to 0, so x is equal to -3. X minus 2 is equal to 0, so x is equal to 2. So zeros of the function is -3 and 2. Vertical asymptote is the value of h, and I don't have here, so it is equal to 0. Okay. The numerator is 0 when x is equal to -3 and x is equal to 2. The denominator is 0 when x is equal to 0. Degree of polynomial p is greater than degree of polynomial q. Let's see here. Yes, the greatest degree here is 2. You remember it, girls, from the first term? The greatest degree is the degree of a polynomial is the greatest degree. The degree of the polynomial is the greatest degree, the greatest exponent. So here I have it 2. Okay, girls? And the degree of q is 1. So now degree of p is greater than degree of q. So if we go back to the previous page, what happens if degree of p is greater than degree of q? There is no horizontal asymptote. If the degree of p, the numerator, is greater than the degree of q, the numerator, there is no horizontal asymptote. So girls, here, the degree up here, let me write it. The degree here is 2, and the degree here is 1. So the degree of p is greater than the degree of q, so there is no horizontal asymptote. Horizontal asymptote is none. Example B, x minus 1 over x squared. So zeros of the function, x minus 1 is equal to 0, so x is equal to 1, so 0 of the function is 1. Vertical asymptote is the value of h. I don't have here, so it is equal to 0. Let's see here the degree. Up, the degree is 1, because the power here, the exponent here is 1. Down, the degree is 2. What happened if the degree of p is less than the degree of q? Let's go to the previous page. If the degree of p is less than the degree of q, so the horizontal asymptote is the line where y is equal to 0. Let's go back to the other, to our problem that we are solving. Yes, here it is. So the horizontal asymptote is equal y equal to 0. Y is equal to 0. Okay, girls? Example C, 2x squared minus 2 over x squared minus 4. I have to factor. I will take 2 as a common factor, divide by 2, so it will be x squared minus 1. X squared, let me write it for you here. When I factor it, it will be 2 multiplied by x squared minus 1. X squared minus 1 is difference between 2 squared, so it will be x plus 1 and x minus 1 here. So 2 multiplied by x plus 1 multiplied by x minus 1 over x plus 2 multiplied by x minus 2. So zeros of the function is -1 and +1. Vertical asymptote is here, opposite of the sign, -2 and +2. Horizontal asymptote, let's see the degree here. Let's see the degree here. Okay, the degree here, degree of p is 2 and degree of q is 2. So the 2 degrees are equal. So let's go back and see what happened if the 2 degrees are equal. If the degree of P is equal to the degree of Q, so the horizontal asymptote is the line where Y is equal to the leading coefficient of P over the leading coefficient of Q. Leading coefficient, if you remember it from the first term, leading coefficient is the coefficient of the highest exponent. So, where it is, yes, here we are. So, it is here, the leading coefficient is 2, and the leading coefficient here is 1. So let me write it. Leading coefficient here is 2, and the leading coefficient here is 1. So here it is the leading coefficient of P over the leading coefficient of Q. It is 2 over 1, which is equal to 2. Okay, girls, it's all about knowing the rules and memorizing all the rules. And if you know it and memorize it well, you can be able to answer all of the questions. Let's watch here the last video together.
All right, let's graph some more and see what we're up to. So here is a rational function. Let's find some nice points first and then see if we can sketch a nice picture of it. So first thing I try to do is to factor if I can. Just because a factored rational function is always more friendly than a non-factored. This negative sign tells me opposite signs here, 3 and 1. Perfect. All right, asymptotes. How about vertical asymptote? That's where the denominator equals 0. That's where x equals 0. That's pretty easy. Horizontal asymptote, well, the degree of the polynomial in the numerator is 2. It's a quadratic. In the denominator, it's linear. It's 1. The power in the top is greater than the power in the bottom. The top dominates, no asymptote. While I'm here, let's find the zeros, where it crosses the x-axis. Well, that's where the numerator is 0, so either x equals -3 or x equals 1. All right, so we can make a table of points, which I already did. I just plugged into here. So for example, if you take -1 and plug it in here, you can evaluate. You can actually do it here or here. Like if you put -1 in here, you see -2 here. And then you put in a -1 here, and you see, actually, this is going to be -1 plus 3 is going to be 2. So 2 times -2 is -4. -4 divided by -1 gives you 4. See? See, just fill it in. All right, let's plot away. Plot away, plot away, plot away. The first thing I always do is draw in the asymptote, since that's going to sort of divide the world up into various pieces. There's only a vertical asymptote. That's on the y-axis. X equals 0. So we cut the world up in 2 pieces. And let's plot some points. So we have the zeros at -3 and at 1. And some other points? Sure, you want other points? I got other points. At -6, 4, 5, 6. I'm at -3.5. 1, 2, 3.5. -3, 1, 2, 3. I am, oh, at 0. Good, okay, that's that. At -2, I'm at 1.5. 1.5. At -1, I'm at 4. Whoa, way up there. And let's take a look at these other points. At 1, I'm at 0. Good. At 2, I'm at 2.5. 1, 2.5. At 3, I'm at 4. 1, 2, 3, 4. Good enough for me. I know there is no horizontal asymptote, so this thing is going to be going out into space and then coming down and rubbing up against, but never touching, this asymptote. And similarly, but in an opposite direction here. So this hyperbola, sort of a wide mouth hyperbola with one vertical asymptote but no horizontal asymptote. Very pretty picture. Let's take a look at another one, because these are kind of like raisins. You can't just do one. Here's one. Now, actually, we can use a graphing calculator to graph these functions, just like you can graph any function. Rational functions, just a special case of functions. So just like you've been seeing how to graph other functions, you can actually use the graphing calculator to sketch a graph of a rational function. Let's analyze this a little bit and then take a look and see what the graphing calculator produces when you actually graph it on the graphing calculator. So without the graphing calculator, we can do a lot. For example, we can find the horizontal asymptotes. That's where the denominator, the vertical asymptotes. Let's do vertical asymptotes first. That's where the denominator equals 0. Well, that's when x squared equals 0, and so I see x equals 0. Horizontal asymptote. Well, notice that the numerator is a linear polynomial. The denominator is now quadratic. Degree is higher downstairs than upstairs. That means the dominating term is going to be downstairs. If you want to fantasize for a second, think about the terms that really matter as x gets big. The plus 3 doesn't matter. It's really just x. X over x squared simplifies to 1 over x. And 1 over x, as x get bigger and bigger and bigger and bigger, what happens to 1 over x? It gets smaller and smaller and smaller, heads to 0. So in fact, we are going to have a horizontal asymptote at y equals 0. Remember this in general, if the degree of the denominator is greater than the degree of the numerator, you always have an asymptote, horizontal asymptote at y equals 0. There's also zeros. The zeros are when the numerator equals 0, and that's when x equals -3. Okay, well, armed with that, we can actually now see if the graphing calculator is going to confirm. Let's take a look at it. So if we graph it on a graphing calculator, we just type in this function, set the window, and we're good to go. Look what you get. Now look at that. Now do you see the asymptote? Do you see the horizontal asymptote? Look where it is. Exactly where we predicted. The vertical asymptote. Perfect. And notice that it crosses the x-axis at just one point. And do you see where that point is? Bingo, -3. We're good to go. Anyway, you can see that the graphing calculator is a powerful way of looking at graphs, or sometimes even just checking your answer. You graph it yourself and you want to say, hey, let me just see if my graphing calculator is as smart as I am. The answer is you're smarter, but it's sort of fun to watch the graphing calculator catch up. Let's try one last example together, and we'll have a little bit of fun. Let's have some fun, you know? Let's get this party started. All right, well, here is the rational function I want us to consider. Let's factor. First thing I always do is factor. So if I factor this, I can do a couple things here. I can pull out a factor of 3. When I do that, I have 3 times x squared minus 4. That's the difference of 2 perfect squares. So I have x plus 2 times x minus 2. Divided by, and that's the difference of 2 perfect squares, x plus 3, x minus 3. There you have it. Now it's all factored. Great. How about some asymptotes? Okay, we can order some of those up. How about the vertical asymptotes? That's where the denominator is undefined. Well, notice there are 2 places where the denominator is undefined. X equals -3 and x equals 3. So this actually is going to have 2 vertical asymptotes. What about horizontal asymptotes? We'll take a look. Notice that here we push, because this is a quadratic divided by a quadratic. So the exponents are the same, the degree is the same. So if you think about it sort of philosophically, you want to find out where you're leveling off. The lower order terms don't matter. Notice that now, since we have a tie, these guys cancel. We go into overtime. We're just left with 3 over 1. You take the coefficient here divided by the coefficient here. There's an invisible 1. 3 over 1 gives us 3. So this is going to have a horizontal asymptote at y equals 3. Are there zeros? Sure, let's plunk down the zeros. That's where the numerator equals 0. Well, 3 never equals 0, but that equals 0 at x equals -2. That equals 0 at x equals 2. Now, believe it or not, just armed with that, we can probably produce a really, really nice picture of this interesting looking hyperbola. Let's take a look at it together. Very first step in my mind, put in the different asymptotes. We have a vertical asymptote at x equals -3. Mark that in with a dotted line. And also one at 3. Equally dotted. And we've got a horizontal asymptote at y equals 3. So we have to go up 3. And what you notice here is that this cuts the world up into 6 different regions. Do you see them? 1, 2, 3, 4, 5, 6. And we're going to be sort of living somehow within these regions. All right, now where do we go from here? Well, let's now insert these points that we know. We have the zeros, so we see that x equals -2 is one of the zeros. So we cross the x-axis at -2. We also cross the axis at 2. And so, and let's see, let's plug in x equals 0, which is an easy point. So here's some easy points. F of 0. If we let x be 0, we just are left with -12 over -9, which is 12/9, which if we simplify is 4/3, which is 1 1/3, so it's a little bit over 1. And so what I see here is that we get a picture where we're going to be asymptotic here. We're going to sort of come up and then come down. So it's going to sort of look like an upside down U. And then what happens in the other regions? Well, again, you could pick some points. I mean, for example, we could pick a point, let's say 4. So if we pick 4, let's plug in 4. What do we get? Well, we can plug into the original thing, or we can use this thing right here. If we use this thing right here, if we plug in 4, 4 plus 2 is going to be 6. And then I've got 4 minus 2, which is going to be 2. So 6 times 2 is 12. And so I've got 12 times 3, which is 36, divided by, and then if I put a 4 in here, 4 minus 3 is 1, and 1 times, and I've got a 4, and this is a 7, so I've got 36 over 7. What is that roughly? It's like 35 over 7, so it's a little bit bigger than 5. It's actually 1/7 bigger than 5. So here's 4, here's 5, it's a little bit bigger, so I get a point right here. Similarly, you can actually see for yourself that if I plug in -4, since I plug in -4 into each of these, I'm going to square them. It's going to be the same thing as plugging in 4. So in fact, I'm going to get the exact same height there. And that's enough to tell me, believe it or not, since I know these are asymptotes, I've got to be hugging up to here, coming down and hugging out to here. I just need that one anchor point to know sort of which region I'm in. Once I knew that, and I see the symmetry, because I'm squaring everything, I'm going to get the symmetric sort of picture reflection over here. So what a beautiful looking hyperbola this is, which really came out of just some basic sort of analysis of the situation, plotting a few points, and we're good to go.
Okay, girls. For the last part here, if we have a hole, the hyperbola, and just wait 1 minute to open the page again. In some cases, both the numerator and the denominator of a rational function will equal 0 for a particular value of x. As a result, the function will be undefined at this x value. If this is the case, the graph of the function may have a hole. A hole is an omitted point in a graph. Holes in graphs. If a rational function has the same factor x minus b in both the numerator and the denominator, then there is a hole in the graph at the point where x is equal to b. Unless The line x equals to b is a vertical asymptote. Graphing here rational functions with holes. Identify holes in the graph of x, f of x is equal to x squared minus 4 over x plus 2, then graph. The hole comes from finding the same term in the numerator and the denominator. Here comes the hole. So when I factor here, x squared minus 4, it is the difference between two squares, so x minus 2, x plus 2 over x plus 2. So there is a hole in the graph where x is equal to negative 2. Why? The repeated term here where x is equal to negative 2. The expression x plus 2 is a factor of both the numerator and the denominator. So divide out common factors. When I divide out the common factors, so left for me x minus 2. The graph of x, f of x, f is the same as the graph of y is equal to minus 2, except for the hole at x is equal to negative 2. There will be a hole here in the graph where x is equal to negative 2. On the graph indicates the hole with an open circle. You will indicate the hole here as an open circle. If we're going fast to answer number 5, identify the hole. So the hole comes if I have the same term in the numerator and the denominator together. So if I'm going to do this, let's factor here. And if I will factor here, what are the two factors? When I multiply them, they will give me negative 6, and when I add them, they will give me positive 1. So the two factors here are negative 2 and positive 3. So let me write them here. X is equal to negative 2, x minus 2, x plus 3. Yeah. Okay. And down I have already x minus 2 down in the denominator. So the whole will be when x is equal to 2. So I'm going to write the whole when x is equal to 2. Okay, girls, and then I'm going to cross the common factor. So f of x, f of x is equal to x plus 3. Okay, girls, let's watch here one more video.
I want us to take a look at one more example together, and this one is one that I really think is fun. Let's see if you think it's fun too. Here's the rational function, x squared minus 9 divided by x minus 3. I want us to graph it. I want us to find the asymptotes. I want us to... First step, always try to factor, right? I'm very systematic, you have to admit. I always try to factor because it allows us to see structure. So what do I see? Well, the numerator is the difference of two perfect squares. That's awesome. Denominator is just awesome on its own. Wow, I can actually simplify, cancel this factor with that factor, and I'm just left with this. Huh. Well, that's just linear now. Well, that's sort of cool. But let's think through like all the steps that we would have otherwise. For example, is there a vertical asymptote? Denominator equals 0? No. Right? This is denominator of 1, so none. Horizontal asymptote. Well, this is x plus 3 divided by 1, which has the higher degree polynomial. The numerator, it's linear. The other one's constant. So that wins out, goes to infinity, so none. Huh, this is really strange. It looks like we're just going to graph a straight line, except for one thing. Remember, the original function is given by this. By canceling this, what's the one point we're not allowed to consider? Well, whatever makes the denominator equal to 0, which is x cannot equal 3. So if this is f of x, it's equivalent to this as long as you promise x does not equal 3. This is really strange, because if you want to graph this, you know what the graph that is. That's a line. It's a line, but x can't equal 3. What does that mean? It means that we cannot have a point at 3. So at 3, we have to actually have what's called a hole. So you can think about just graphing this line normally. How would you do that, by the way? Well, it has a y-intercept of 3 and slope of 1. So it's, 1 over 1 up. 1 over 1 up. 1 over 1 up. But I'm not allowed to equal 3. So I put a hole there. But all the other points are okay. So when I take my straight edge and produce the line, I'm actually going to see a really cool graph. I think this is so cool. I really hope you think it's cool too. It's a straight line that's been punctured. It's a line with a hole. And the location of the hole is actually at the point where we're undefined, namely when x equals 3. It's not an asymptote because things cancel away, but it's just a hole. So the graph of this thing, which looks like it should be a hyperbola, is actually a line that's been punctured with a hole. Isn't that cool? I think that's so awesome. So whenever you can actually cancel and you're ending up with a line, then in fact you just graph the line, but you have to erase the one point, the point that's actually not allowed. No asymptotes of any kind. It's just a regular old-fashioned line with a hole. So it's sort of interesting. If you ever wondered, gee, what's the formula for a line with a hole in it? You might think it's sort of hard to write down. It just involves a rational function. Pretty cool. Anyway, enjoy thinking about the graphs of rational functions. Look at them, admire them. They're beautiful hyperbolas. You'll love them for yourselves. Find asymptotes, find intercepts, have a lot of fun, be careful, and enjoy graphing them on your own. I'll see you soon.
Okay, thank you, girls, so much for listening, and I hope we're going to answer your homework without any problems. And if you have any problem, feel free to contact. Thank you so much. See you.